Nope. Do you introduce me? No, I introduce myself. Hi! Yeah, everybody wave like this so you're all awake. Good. Okay, my name's Phil Wadler. Yeah, you can stop waving now, Sophia. Or not. Right, are there any questions? Not yet. Okay, so some people begin their lecture by saying, can you please hold all questions to the end? I will do the opposite. I will say, will you please not hold all questions to the end? This is supposed to be a friendly environment. And very often, right, I can skip over not saying something that, because it's obvious to me, but it's not obvious to you. But it's important for you to learn. So this is supposed to be a learning experience. So if I say something that you don't follow, please ask a question. Or if there's something you want more detail of, please ask a question. I might ask you to save it to the end, but it's much better for you to ask it. I'll feel like I've succeeded if I get some questions during the talk, because that means somebody is listening and engaged. So has that inspired any questions yet? Okay, so my name's Phil Wadler. I work at the University of Edinburgh, but I also consult for a cryptocurrency firm called IOHK. And what Jan and the others invited me to come talk about is the work I'm doing for IOHK. So I'm going to give you a very high-level summary of some of the work that we're doing there. So first let me tell you why I am so excited to be working for IOHK, and that's because the team there actually publishes papers. So it's a cryptocurrency firm. One of the key things about the cryptocurrency is that it's based on a protocol called Ouroboros, designed by my colleague Agelis Kiaias at Edinburgh and his colleagues. And so this is the peer-reviewed paper that describes Ouroboros. The key thing about Ouroboros is that it is not proof of work, it's proof of stake. So proof of work is what Bitcoin and Ethereum and many other cryptocurrencies use to decide who gets to issue the next block. It's a nice, simple way of deciding who gets to issue the next block, but it's energy intensive. Right? So I guess most of you will know that cryptocurrencies literally use as much energy as a small country deciding how to issue the next block, and that's because they're using proof of work. So proof of stake is much more efficient. It basically says, we will roll a dice to decide who gets to issue the next block, but the dice is weighted, so the more of the cryptocurrency you own, the more likely you are to get picked. And then there's a step on top of this which says you can delegate your currency to somebody else that will actually do the issuing. But this is supposed to lead to then having a decentralized system. So they're in the process of implementing all that, yeah. So Cardano, which is the blockchain product that IOHK offers, is up and running, but what I'm going to show you is what's planned for smart contracts for Cardano, which is not up and running yet. And currently it's using what's called a permissioned blockchain, which is there are few vetted people that issue blocks, and it's not yet fully decentralized. Question?
Hi, you might have already mentioned it, but if it's weighted towards people who own more, how do you stop monopolies?
Right, so if it's based on who owns stuff, how do you stop the monopoly? Well, the hope is that you won't have people buy up more than half the cryptocurrency, because then they could manipulate things. And what prevents that is just that it's reasonably valuable, so you'd need several billion dollars to do that. But yeah, that's an issue that there's, right, you need to look at the mathematics of that, and there are people that do that. I'm not an expert on that. But yes, there are real issues there. That's quite right. Good. Any other questions? Okay, so it's proof of stake. Here's the paper on the proof of stake algorithm. And here's another paper on Ouroboros, and another one on Ouroboros, because they've done quite a few of them, and another one. And there's a paper on Marlowe, which is one of the things I'll be telling you about. And there's just a functional Perl that was published by somebody at IOHK. The reason I'm putting all these papers up is IOHK actively wants what they do to be based on published peer-reviewed research. That shouldn't be surprising. But I don't know any other firm, not any other firm in the cryptocurrency space, any other firm that has publicly said what we want is for everything we do to be published and peer-reviewed. You're shaking your head. Okay, so I know one other firm, good, also in the crypto space. But by and large, there are very, very few of them indeed. So I only knew of one, now I know of two. Right, and this is amazing, right? Because all of science, the whole thing that makes science work, is peer review. Right? Without peer review, it'd be much harder to guarantee that the science is correct. But nonetheless, right? So if you've got big companies like Google, and they will let the people there publish. So MapReduce was published, but they didn't say we want it published and peer reviewed before we use it, so we know it's right. Right? They were just allowed to publish afterwards. So there are some firms that allow people to publish. Microsoft actually has a research lab, which is great, where they are encouraged to publish. But by and large, business doesn't work this way. So Charles Hoskinson, who's the CEO of IOHK, of course, he hopes that this will succeed and it will make lots of money, but he points out if it does, maybe then people will pay attention and look at the techniques that IOHK used and do things like decide to rely on peer review. But so this is why I like working for IOHK, because they actually think peer review is a good thing, and it's unusual, and wouldn't it be nice if it weren't unusual? The other reason I like working for IOHK is that they write all their software in Haskell. Not all of it, but a large chunk of their software is written in Haskell. So the main software for the Cardano blockchain is written in Haskell. They've now got another bit that they're writing in Rust. But at first, everything was in Haskell, and still a very great deal of it is in Haskell. And also, they do amazing things like they write down the spec first. So they had a formal spec team, and the formal spec team was charged with writing a spec of what had already been written. And they said, no, we shouldn't do it that way. And again, right, IOHK agreed. So now they actually write down the specs of the software first. Yeah, question?
Just can you qualify specs? What does it mean to write specs first?
Okay, so I've not prepared the material on that. But basically, they just write down a specification that's in LaTeX, right? Just a bunch of maths in LaTeX. So it turns out a ledger is fairly easy to describe formally, and then they go on, they describe things like how the wallet monitors the transaction that it sees so that it knows what the current balances and accounts are, and that they're modeling things like the wallet only tracks certain accounts and things like that. So that's what the formal spec describes. It's all fairly straightforward, just done in set theory. But there is a spec then that they can work from. Okay, so the other thing, so they use formal specs and they use Haskell, so I'm excited about that. And you guys, I think, will know this, but when I talk about this, I stress, why is Haskell interesting? Because not everybody in the world knows that. So there are examples of Haskell out in the real world. I think most people here will be familiar with these. So Facebook, of course, uses Haskell. Simon's actually sitting in the room. So every post gets checked for whether it's spam by Haskell. That's the main use. Is that right, or am I missing a major use? Well, should I just describe it as filtering, searching for spam, or should I describe it some other way? Sorry? Abuse detection. Okay. Sorry, they'd be checking that there's not enough of it, or that there's too much? Right, so Facebook uses Haskell, and of course the whole point is that since it's a functional program, it parallelizes easily, and Haskell is massively parallel, which you need to deal with that much volume. Another example is SEL4. How many people know about this one? Okay, not all of you. So SEL4 is an operating system for mobile phones, and there's a team at what is now called Data 66, I think, in Australia. They had another name previously, but they've gone about writing out all the specs and then deriving an operating system that matches all the specs for things like security, so that you know certain kinds of information doesn't leak. And again, the way that they implemented this was they wrote out the whole operating system in Haskell, translated it by hand to C, and then wrote out proofs that the C and the Haskell are doing the same thing. But Haskell was essential in getting this all to work. So they're now working on another language called Cogent, which is again a functional language similar to Haskell, from which they can automatically derive these proofs, which is a good idea. But the first version was done in Haskell with proofs by hand that it's equivalent to C. And then, of course, Haskell's quite heavily used in the financial world. How many people knew about Haskell's use in the financial world? Yeah, that's about what I expected. So these are all the banks I could find, or financial firms that use Haskell. And of course, other functional languages are also used because banks value the fact that you can write a functional program quickly and it's likely to do what you expect. And in the banking world, especially where they're doing machine trading, it's very important that you can write it quickly and that it actually behaves as expected. Okay, any questions about any of those? Okay. And then the other thing I want to say is the obvious thing about smart contracts, right? The reason that they are great for our field is, right, well, we want to do things like prove properties of programs, which is a lot of fun and gives you high assurance, but is very expensive. So basically, it's only for something like an operating system that lots of people are using, where you can amortize the cost, that you might even think of proving it correct. But, yeah?
What is the difference between a smart contract and a regular program?
What's the difference between a smart contract and a regular program? So, that's an excellent question. So smart contract is just the name for a bit of code that is attached to a piece of cryptocurrency. So it's a script attached to your cryptocurrency, and it determines when you can spend the cryptocurrency, in effect. So an example of a smart contract, I'll show you more about this one later, is a crowdfunder. So you can say, I want to raise this much money by this date, and the contracts let you pay in the money, and the contract specifies that this must be raised by this date, and if it is, it'll go to the person that's trying to raise the money, and if it's not, it'll be refunded to the people that contributed the money. So you can do that now. You can do that through Kickstarter or whatever. But when you do it through Kickstarter, you are, of course, trusting that they will do what they say. So when you do it with a smart contract, you publish the smart contract, and now instead of trusting, you can read the smart contract and check that's what it says. The smart contract is distributed, and there's no way of revoking it, which, by the way, is a problem. If you discover a bug in your smart contract, there's no way of revoking it. Once it's published, that's it. And this is great because one problem with contracts is, right, say you're a small farmer and you have a contract with a big supermarket, and you hand them over your milk, and you've got a contract, and the contract says they will pay you this amount for the milk. You hand over the milk, and then they can say, oh, we're not going to pay you until 2 weeks from now. Right? And this happens all the time. This often happens with contracts, is one party or the other just won't obey the contract, and then you say, yeah, but you signed a contract, and they say, well, what are you going to do, sue me? And suing is a very expensive process. So the nice thing about a smart contract is it will do exactly what it says. So if something fits in the realm of a smart contract, this is fantastic, because you no longer need to worry about going to the court, as it were. You still might want to have some adjudication system. You still might want to be able to go to the court. And one big question is, how do you get smart contracts to actually interact with the proper legal system, which is a very important question that people are looking at, which I won't address partly because we don't know the answer yet. Right, but there are lots of things connected to cryptocurrency, such as this question, such as the question of how do you regulate it, which are very important and which people are beginning to look at. but which I won't say more about because it's not clear where you have to go with that. It's just clear you have to go somewhere. Yes?
So when a smart contract involves something in the real world, such as the delivery... So when the smart contract involves something in the real world, such as delivery of milk, and that's a condition, term, whatever, in the smart contract, how does that work?
Right, so how do you connect, the question is how do you connect a smart contract to the real world? The answer is we don't know yet, but the ideas are all along the lines of things called oracles. So let's say you've got a smart contract that depends on the price of oracle. Let's try that again. Let's say you've got a smart contract that depends on the price of oil. Then it will be built into the smart contract that it queries a particular address in the system, and that must be an address that you trust to actually publish the correct price of oil. So yes, there's trust involved there. So although the great idea of smart contracts is they're self-enforcing, you still need trust for things like confirming that a physical item has been delivered or getting hold of something and so on. And of course, you can have lots of eyeballs on the oracle, so people can know if the oracle is lying, but ultimately there are various places where you need trust in the system. Another place I was about to mention is it's great when you can have a smart contract that's self-enforcing, but lots of the most important contracts we have are things like loans. So the way a contract can be self-enforcing is everybody pays in the money at the beginning, and then the contract decides how it's paid out. Or for something like the crowdfunder that I just described, you're not all paying in at the beginning, but nonetheless you're following rules about how it's paid out, and you know what will happen, and the contract can be self-enforcing. But a loan is somebody pays some money back at the end. The whole point is you don't have the money at the beginning. One party has the money at the beginning, the other party needs the money, and then the second party is supposed to pay the money back when they're done. But you can't make paying the money back when you're done self-enforcing, because the money's not there yet. So smart contracts are great for the places where they apply, but they don't apply everywhere. And one thing that the team has discussed is, maybe, again, because you need trust here about being paid back, you get somebody that says they will pay back the loan who you trust, that it is an endorser or indemnifier for the other party. And maybe we can layer those on and so on. But there's lots of open questions here. So I guess most people will have heard the saying about smart contracts. So what everybody says about them is they're fine. The only two things you know about them is they're not smart and they're not contracts. And we've touched on that, right? That how they interact with the legal system is unclear, but there will need to be a way for them to do that. But the other thing, right, is the main system that has smart contracts now is something called Ethereum. Ethereum is a very interesting system. And one of the things that's interesting about it is here's a list of all the frauds conducted against Ethereum that have stolen money from it. So a very famous one is the DAO reentrancy bug, which was early on and stole a very large amount of Ether. And since each Ether is worth like $100 US, this is a lot of money. And there's some other ones down here that are a lot of money. Some of these occur from things that any programming language designer would have said at the beginning, don't do that. So Ethereum uses 256-bit words, and if you overflow the word, it just wraps around. There's no error raised or anything else. And there are quite a few bugs and also frauds that depend upon that. Right? So literally, more than millions of dollars have been lost just due to overflow errors. And of course, that's something that anybody in this room would say, no, it should raise an error if there's an overflow, rather than just silently wrapping around. But other things, like the DAO reentrancy bug, which I won't go into in detail, some people in concurrency theory said, oh yeah, we knew that was a problem. But when I first saw that, the DAO reentrancy bug, I thought, wow, how would you ever figure that out in advance? And lots of people, such as Yanis Maroudakis, who's I think not in the room, who is here, Right? So Yannis has written a great system that once you know what the bug is, it can go search for similar bugs. But the more interesting question is, what property would you want to validate of a system so that you know you need this property, and you validate that property, and that catches the existence of the DAO bug? That's much harder. So a very important question is, what kind of properties do we want these systems to have? So there are a few obvious ones. You want to be sure that all the money that goes into the contract comes out again. There are bugs where that has not happened, where money goes into a black hole and you can't get it back out of the contract. And because it's a contract that you want to be self-enforcing, a very important property is no one person can lock it up. Right? So if at one point the smart contract says, okay, and now we wait, right, it's a contract between Alice and Bob, and at this point Alice has to do something, and Alice just decides, no, I'm not going to do that. And then the contract is locked, and Bob can never deal with his part of the smart contract and get out what Bob was expecting to get out. So a very important property of smart contracts is that no one individual can lock it up. So being a programming language person, of course, I call these properties preservation, that you don't lose money, and progress, that no one person can lock it up. There's an interesting, very simple smart contract language called BitML for Bitcoin, where they've actually independently came up with those properties and validated them. Sorry, that's a higher level language like Marlowe, which I'll show you in a minute. So there are some interesting things to be done, but we're just at the beginning of this process. It's not at all clear what kinds of properties one should go about proving for smart contracts. One of the things I hear in this field is people often say, oh, we know about validation, we'll just go off and validate the smart contracts. Well, yes, but first we have to figure out what is it we want to validate. And I think that's not completely clear yet. So I think there's a lot of interesting work to be done. So the point to make is just that it's well known that you can easily lose lots of money in a system like Ethereum. Some of that is because some parts of the system are poorly designed. Some of that is because the problems are hard and we don't understand them yet. But it's worth stressing that in front of this audience because there are lots of interesting problems here for programming language people and verification people to look at. So that's probably the most important takeaway of the course is right now the systems are leaking lots of money, right? It's just like clockwork. You will expect every 6 months to see another story about another few $100 million being lost in Ethereum. So people know there's a real issue here, and it means you can have something that is actually, takes some work to use, but it's still worthwhile for people to use it. So this is actually a very good application area for us. Okay, so you want to have smart contract languages. We've got two at IOHK. One is called Marlowe. It's been being designed by Simon Thompson and others at the University of Kent. It's named for Christopher Marlowe, who's from Kent. And it's a domain-specific language. These are slides I stole from Simon. So it's just a domain-specific language for dealing with contracts. And actually, I'm going to skip over these and show you this. So is Simon Peyton-Jones here, or is he in a different room? He's in a different room. But this is a paper by Simon and Jean-Marc Eber and Julian Seward that appeared in ICFP in 2000. I know it was 2000 because I was the program chair that year. This was one of the first functional Perls to appear in ICFP because I introduced them that year. This could have just been a research paper, but they were generous and wrote it up as a Perl. And this was just a small domain-specific language for writing down financial contracts. Jean-Marc Eber later founded a firm, Lexify, to do these. Oh, sorry, he'd founded it by then. And his claim after this was before the financial disaster of 2008, but after, right, that was caused by lots of complicated financial instruments that nobody knew how to value. And so he made the point, if you write these instruments down in a domain-specific language, you can value them automatically. and you get a real sense of what's going on. You can't just hide problems in your financial instrument. So I still think that's a good idea, but it's not one that's caught on widely. It's something that we should be doing, but one of the many responses to the crisis of 2008 that has not occurred. Right? There should have been more regulation after, and they should have been things like this technical solution of trying to write out your financial contracts. So anyhow, this is small domain-specific language, and there are quite a few different ones that have been based on the same ideas, and Marlowe is one of them. And one of the important things is, as well as writing out your smart contract that you can execute, you can automatically do things like get a valuation of it or analyze it for properties I just discussed, such as that no one person can halt things and that all the money that goes in goes out. And in fact, Marlowe is designed, right, it's not Turing complete, and Marlowe is designed to ensure those two properties, that every Marlowe program that you write, it's either guaranteed or very easy to check that it satisfies those properties. And you can use it online. There's something that used to be called the Meadow, and now I believe is called Marlowe Playgrounds, where you can go and write a little Marlowe program online. This is actually Haskell code that evaluates to a Haskell data structure that describes the program, and then this is using Blockly to write down the exact same program. So you can use either way to write down your domain-specific program. So it's a little small language, and in fact, I've been in discussions with Simon where I said, oh, this bit looks too complicated to me, can't we change that? And we're looking at how to change that. Right, so here's Meadow running. I'm actually going to skip for a moment. So in order to evaluate, well, what would be a good way of designing it? So IOHK has partnered with a firm called Actus, and Actus has their own taxonomy of financial contracts. So one of the things we're doing is we're going through all these different kinds of contracts in their taxonomy and saying, okay, which of these can you write out in Marlowe and which can you not, and why? So some of them you can't because they're things like loans, and I already explained why that would be an issue. And then other ones we think we can't. So most of this can actually be covered by Marlowe, but we're going through systematically trying to work out what we can do and what not and why. The other thing I want to say about using high-level contracts, so there's another firm called DN Digital, which Fritz Henglein in Copenhagen helped found, and they have yet another one of these languages that's a descendant of the Peyton-Jones and Eber language. And they've got people using it on a permissioned blockchain. So not one that's distributed where anybody can issue blocks, but one where you have a group of people that are you trust who are issuing blocks. And the point there is that because they've got this high-level language, that instead of needing a developer, right, here's your developer, to go in and write the contract for you, that instead it can be written by somebody called, so instead of having a business analyst work out what you need and the developer implements it and the tester tests it, right, you just have the business engineer knows enough to write in the high-level language. So the business engineer works out what you want the contract to do, and then they can actually write out the contract. And the important thing is DN Digital actually has experience with people doing this sort of thing. So this is really the big advantage of having a domain-specific language. Right? You can't do everything, but you can get it to be done by high-level people like business engineers rather than having to hire developers. There's what a business engineer looks like. Okay, so that's Marlowe. Any questions about Marlowe? And I'll go on and say a little bit about Plutus. So Plutus is our Turing complete language, one in which you can do anything. As I mentioned, you'd like to actually verify that the code does what you want. So we do not have these verification techniques in place yet, but clearly you want a nice, simple language where you understand the semantics thoroughly. And of course, the advantage is using a functional language. So what we've done is the high-level language that you use, it's called Plutus, so this is Plutus. I hope this doesn't violate the code of conduct for the conference. But this is Peace, the woman is Peace, and she is feeding her milk to Plutus, who is the god of money. And there's the whole picture. This is by Rubens, and it's in the National Gallery nearby, so you can go have a look at it. So that's why it's called Plutus. Turns out there's another completely different financial language also called Plutus, but just the people at IOHK told us it will be called Plutus. We said, fine, it's called Plutus. They can sort out that there are two different systems with that name. So the way Plutus works, so this is a very nice programming language observation that was made not by me, but by Manuel Chakravarti, who works for the Plutus team. He's the team head. So here's an example of some code for Ethereum. So the language in which you write for Ethereum that compiles down to the EVM, the Ethereum virtual machine, is something called Solidity. It's a little object-oriented language. And here's 81 lines of Solidity to do a crowdfunder, the thing I described before. Something where you want to pay in a certain amount of money by a certain day, and either it goes to the person running the project, or it comes back to the people who've donated if not enough money has been raised. And you can write that out in 81 lines of Solidity, but what Manuel drew my attention to is that this particular example also has 149 lines of JavaScript, which is what runs in the wallet on your machine and drives the Solidity, right? You need some way of interacting with what's on the chain. So your smart contract isn't just what's on the chain, it's also what's off-chain. So you need off-chain and on-chain code to interact in some way. So what we've done is all the code is written for us in Plutus in Haskell. And then the key point is that some of it's written in green and some of it's written in blue. And what this means is this green stuff is the stuff that's going to run off-chain. So you don't need to trust that as much, right? That program you can change. You can't trust it, right? You don't know who's running it. What you know about is what's been registered on the blockchain, the thing that controls who gets to spend the money. And that's this stuff, which is in blue. And it's in blue because it's written between these funny brackets. So here you've got funny opening bracket, and here's a funny close bracket. And then this is all Haskell still, but it compiles to a simpler language that runs on the blockchain called Plutus Core. And this is essentially just a tiny functional language, but it's small enough that we can actually validate it, which the Haskell compiler, you cannot. So that's nice. So we get out something small that you can read and then validate. But all the code is written in a single language, Haskell. And I worked on a system, Lynx, that was about programming the web. It was the same sort of thing, right? In the web, you have code that runs on the server and code that runs on the client. But what you want is to have a single language where you write both of those, and then some runs on the server and some runs on the client. This is a very similar idea. And again, we've got a playground, so you can try it out. So if you just type in Plutus Playground, you will find this easily, and you can see Plutus programs and execute them on the web, and then you can also download our development kit if you want to do that. I've got 10 minutes, so I'm going to, actually I'll skip over that one. It's a very interesting thing, but I'm going to skip over it. I'll tell you just a wee bit about Plutus Core. So, yeah.
Excuse me, I have a question. So you showed this client in JavaScript for Solidity. Strictly speaking, one can write a client in Haskell too, right? And interact with Ethereum through ABI from Haskell frontend, which runs off-chain. Just the point that Solidity is not an inherent part of Ethereum. I'm sorry, JavaScript client is not an inherent part of Ethereum platform.
Correct.
You can have a client in Haskell as well. And
you can write the client in whatever you want. That's right.
Presumably you can also have a client in JavaScript for Cardano.
You could, yes. Right, but this is the system we're providing to people. So right, rather than letting somebody else come up with a nice way of doing it, we're trying to provide as standard a nice way of doing it. But that doesn't mean people couldn't come up with other ways of doing it.
Okay, and I have a second question. Probably you're going to answer it right now. So Plutus Core is what is being run by the validators. So that's the backend.
So that's
the backend language. So there is no further virtual machine that it compiles down to.
That's right. Plutus Core is directly run on the blockchain. That's right, by the validators. And what is it? It's just system F omega. So we had a larger language, right, with things like data types in it. And I said, well, wait, maybe we can get away for really small language. This is going to be slower, probably 3 times slower than actually having things like data types in your language, right? Because instead we compile everything into Scott representation, not the church representation, because then predecessor takes time proportional to the size of the number, but Scott representation. And so it's a very tiny language. Doing that is probably about 3 times more expensive, which could be an issue, except pretty much all your time is in fact spent on cryptographic primitives. So the fact that your smart contract script is a bit inefficient to execute, we think won't matter, although we still need to do the measurements to confirm that. And to be honest, right, we just did the first set of measurements and it wasn't as drowned out as I thought it would be. So we might discover that this is too simple. But for the time being, we compile into a very, very simple language indeed. And this is the virtual machine for it. And in fact, the publicity people for IOHK decide to then print it on a napkin to show how simple our virtual machine is. And we've also, one of the nice things in the cryptocurrency field is, as I said, right, errors are expensive. So there's actually a business case to do formal validation. So we are not the only firm that has done a formal spec in a proof assistant of our core language and then done formal proofs that it is type safe. But we are one of them. And in fact, we got to hire James Chapman, who's sort of the world's foremost expert on AGDA specs of lambda calculus, to do this. So I did the first sketch of it, and then James filled in everything. But we have an actual AGDA spec of system F omega, which means Plutus Core. And in fact, the whole spec has now been done, and he's proved type safety. He's proving some other things. But among other things, because it's AGDA, and it compiles down to Haskell, we could just use the same implementation for all the primitives that we already had in Haskell. Right, so system F omega, of course, you allow primitive data as well, which is how we do things like numbers. So we can test it. We now have 2 implementations. We have the one done completely in Haskell and the one done in AGDA with the primitives in Haskell, and we test those against each other. This is one of my other colleagues, Roman, saying how great James's work is. I'll skip over that. I'll very quickly advertise. Of course, I'm excited that we're using AGDA because I've just written a textbook in AGDA called Programming Language Foundations in AGDA, which is freely available on the web. So if you want to learn AGDA, please go have a look at that. And then we could use that as a model for what we did. That actually won the Best Paper Award at the Brazilian Formal Methods Symposium, SBMF. So that's me holding the certificate for Best Paper. So there is where Programming Language Foundations is if you want to do it. And I'll just finish by saying the obvious thing, right? Why is system F omega great? Because, of course, it was written down twice. So lambda calculus was actually discovered twice. Once, both in the 1930s, once by Alonzo Church, who wrote it down, but then at the same time, Gerhard Gentzen was doing natural deduction, and 30 years later, thanks to the work of Haskell Curry, sorry, not Haskell Curry, thanks to the work of William Howard, what's now called the Curry-Howard correspondence, we discovered that these 2 things are in one-to-one correspondence. And of course, it's not just these 2. So you've got System F, designed by Jean-Yves Girard, and polymorphic lambda calculus designed by John Reynolds. And those also, right, they were completely independent inventions or discoveries, if you will, of the same thing. And this is our core language for Plutus. So how do you make sure that your language won't be obsolete in 40 years? Use one that was invented 40 years ago. And use one that was discovered twice. So that basic idea is called the Curry-Howard correspondence, or propositions as types. And if you want to know more about that, I have a paper in the December 2015 Communications of the ACM on that. And I will stop there. I'm not going to rip off my shirt, sorry.
questions. If the microphone is coming to you.
Thank you, Phil. We have discussed in the past how you will be representing money and the transfer of money, which in my thinking is a stateful operation. And your answer at the time was easy, use monads. So I'm going to ask the same question again. In a system where, which is primarily about change of state, is it good to make the programmers use something quite sophisticated like monads in order to represent it?
It's a very good question. So, right, Haskell's a functional language, but you really want to look at changes of state. So I'll thank you for this, because it gives me an opportunity to go back to the bit I skipped over. So it turns out, right, in Ethereum, you represent things with accounts. I'm not going to go through this in detail. But in Ethereum, you represent things with accounts. So you say, right, the first thing that's going to happen, the first transaction takes money from O and gives it to A, and money from O and gives it to B. So we're giving 6 from O to A and 4 from O to B. And then next we'll give 3 from A to C and so on. So you've got these transactions that happen. And the important thing is, right, they could happen in a different order. Right? And then sometimes things will become invalid because not enough money will have arrived yet. So that's your imperative way of representing things. In Bitcoin, and also in Cardano, we use something called UTXO, unspent transaction outputs. And you've got this graph of transactions where each transaction has some outputs. This is money that can be spent. And right, what lets you spend the money? Well, if the money is labeled with a public key, if you have the corresponding private key, you can spend the money. Or the money is labeled with a smart contract written in Plutus, and if you provide the correct input to that smart contract, then you can spend the money. So here, this is an output of this transaction and an input to this transaction, and then this one has outputs and so on. You can only file the transaction once you know where the outputs are that are its inputs. So the inputs are references to the outputs of preceding transactions. So you get this little functional graph. The interesting thing is, because it's a functional graph, you don't need to worry about the order in which things happen. You know that the inputs to this will be from here and here. And this is important because executing a program, of course, takes time. It's executed by the validators, the miners for the smart currency. So you need to pay them money to execute your contract. The amount of money you pay in Ethereum is called gas. Everybody has a pretty similar mechanism. We will have a similar mechanism for Cardano. And the point is, you need to know how much gas it will cost. Right? If you don't provide enough gas, they will charge you for it, but it won't execute. The transaction won't happen. So you need to know in advance how much it will cost. In Ethereum, you can't, because you don't know what other transactions have happened before yours. In Cardano and in Bitcoin, you do know exactly how much it costs, because you know exactly what your inputs are. So you know all the relevant information, so you know exactly what it will cost. That's very important, right? You don't need to guess at how much it's going to cost. You know exactly how much it will cost. You can work that out in advance by just running it on your own, simulating it. So that's a very important advantage of doing things functionally. You could still argue philosophically about whether functional is the best way to do it in what is a world where you're moving money around. And it seems like a good way to think about that might be imperatively. But there is this one technical advantage from doing it as this functional graph, which is you know exactly what's going on. You can't have race conditions in the graph because you know exactly what all your inputs are. So that's a very big difference from the transactional way that Ethereum does things. So we've chosen to do it this way. There's also a disadvantage, which is how do you make sure the smart contract continues? Well, the answer is the smart contract checks the transaction before it says it can spend the money, and it checks that one of the outputs is labeled with the same smart contract. I think that's a sort of fragile way of perpetrating things. In that sense, an imperative model, I think, is clearer. But there is a big technical advantage to doing it functionally, which is something I'm sure this community appreciates. But what's the right way? The answer is we will continue to debate it.
But I think don't assume that because the community comes from a certain area that it will be blind to arguments.
Oh no, I wouldn't want to
Okay,
assume that at
good.
all.
Right.
Okay, perfect. Thank you. Thank you.